Professor, can you hear me?
Yep, can you hear me?
Yes.
All right. So it looks like it's just about 8:30, so let's get rolling. Good morning, everybody. I hope that you all had a nice weekend. So we are just continuing our chapter 3 work. I do want to remind you that on Thursday, there is a review session to just do more practice derivatives. So if you feel like you could benefit from some extra practice, feel free to stop by the review session. It's from 5 to 6, and the link is in Moodle. So today we're going to be talking about something called the chain rule. And what we've done so far is we've reviewed all of what's called the basic derivatives. And basic does not mean easy. Basic means foundational. And so now that we have all of those derivatives, we're going to start to put them together to look at more complicated functions and think about how we might find the derivative of those more complicated functions. And so today we're going to start with the chain rule. And just as sort of an overview, the chain rule deals with functions that are specifically composite functions. So I want you to think back to chapter 1. We were learning about composition, how to plug one function into another. Well, now the question becomes, if we have a composite function, how do we take the derivative, right? Because we only know how to do derivatives of single terms. So that's what we're going to be looking at. This has a lot of pieces because there's a lot of different types of chain rules that we can do. So we are going to be doing this today and on Thursday. So we won't finish all of the chain rule examples today. We'll do some of them on Thursday. And this week only, there's only one mini quiz, and it's due on Sunday. So there's just one mini quiz on the chain rule, and then that'll be due on Sunday. So let me switch over to the dot cam here. Okay. So when we talk about the chain rule, one of the most important things is recognizing the function and recognizing that we have to use the chain rule. So there's going to be other types of functions we look at that are not composite functions, but that's sort of the first step in everything we do, is that we are looking for a function where one function has been plugged into another one, right? So if we can recognize that, then we know that we have to use the chain rule process. So because it's a composite function where one function is plugged into another one, and we're assuming that both of these have derivatives and all that stuff, what happens is if we make a small change in one of the functions, it impacts the entire function, okay? So there's some sort of background on the chain rule here, but I want to jump down to these. These are sort of the key pieces. If you're interested in sort of what's happening in the background a little bit, we'll do quite a bit of it today, but this is sort of the formal definition that we're thinking about here. So what you need to know here is that if we are thinking about finding the derivative of y with respect to x, okay, and our function is a composite function like this, then what we can do is we can split it up into two different derivatives and multiply them together, much like we do with fractions, things of that sort. And we're going to look at sort of an example down here in a minute. But also in the other notation, so this is sort of the Leibniz notation, if we are going to take the derivative of a composite function, the general chain rule derivative looks like this: f prime of g of x times g prime of x. So this is the derivative of the outside function, where the inside stays the same, times the derivative of the inside function. And so what we're going to do is we're going to do a whole lot of problems today where we're applying this method as well as this method, right? And we're going to look at how we set these up, how they differ, how we can apply them, and things like that. But before we get there, let's think about how the chain rule might come up and why we might want to use it. So we're going to look at this example. We're not going to do anything out, but just to give you a sense of how this would be set up. So suppose the amount of gas that a vehicle uses, G, in gallons, depends on the distance traveled, S, in miles, right? So if you're going to drive 10 miles, you use a different amount of gas than if you drive 50 miles, right? The distance traveled, S, depends on time in hours that the vehicle is driving, right? How far you go depends on how long you've been driving. So distance also depends on time. So if 5 or 0.05 gallons of gas is used for each mile traveled, and the vehicle is traveling at 50 miles an hour, then we can calculate how fast gas is being consumed. So if we know the rate at which gas is being used for miles, and we know how fast the car is traveling in miles per hour, then the way that we would figure out how much gas we're getting over time is how quickly gas over distance is changing, right? So 0.05 gallons per mile times how quickly the mileage is changing, right? The position, so miles per hour. So by multiplying these two rates together, so the 0.05 and the 50, that's going to tell us how quickly the gas is changing. So the idea is that we have two different functions being put together, but the way that each of those functions is individually changing impacts the overall function. Okay, so that's just sort of like the background of what's happening. How do we actually use this? How do we figure this out? What do we do with it? Okay, so we're going to start with this definition here. So f of g of x, if we want to take the derivative, is f prime of g of x times g prime of x. So we're going to start with some examples where we have to apply this and figure out how to put all of these pieces together. Okay. So here we're going to start with an example. Use the information from the table below to answer the following questions. So notice that in our table, we have values for f of x, for g of x, for f prime of x, and for g prime of x. And then we have information at 0, 1, 2, and 3. So we want to determine if the function y equals f of g of x, so this is a composite function, is increasing or decreasing at x equals 3. Okay. Part B, we want to determine if y of g of f of x is increasing or decreasing. So notice that the composition is different. This is f of g of x, this is g of f of x, and we'll talk about that in a minute. And part C is to find the equation of the tangent line to this function at x equals 1. Okay, so this is not super easy. So remember, if we have f of g of x, and we want to take the derivative, we get f prime of g of x times g prime of x, right? Similarly, if we have g of f of x, and we apply this formula, we're going to have g prime of f of x times f prime of x times the inside. So we need to figure out all of these values based on this table to answer these questions. So for part A, I want to remind you that for the function to be increasing, our derivative needs to be positive. For it to be decreasing, the derivative needs to be negative. So we need to figure out the derivative at 3 for f of g of x and g of f of x. So here, what we're really finding here for the first one is f prime of g of 3 times g prime of 3. That's the derivative, right? That's up here, but I've plugged in a 3. So we have to figure out all those values from the table. For the second one, we're considering g prime of f of 3 times f prime of 3, again, using values from the table. And then for the last one, I want you to see if you can figure out how we might find the equation of the tangent line based on what we know from parts A and B and what we know about that process in general. Okay, so I'm going to give you about 2-3 minutes. See if you can work these out with values from the table. See if you can figure out part C. Feel free to check in with someone near you, and then we'll go through it together in about 3 minutes. All right, take about 30 more seconds. All right. So again, the first step of part A is figuring out that we want to determine the derivative and see if it's positive or negative to answer this question. So we have to sort of figure that out first. Once we know that we need the derivative, we sketch out what the derivative would be using our formula. And now we need to figure out the values. So here in this first term, this is still composite. So we need to start from the inside and work our way out. So we start by finding g of 3. So we go to the g column, we go down to 3, and we get the value of 2. So now I have f prime of 2 times g prime of 3. So again, I just substitute in the value of g of 3 here. So f prime of 2, I go to f prime, I go down to 2. That gives me a value of -1 times, now g prime of 3, I go to the g prime column, I go down to 3, and I get -1 times 1, which gives me -1. So I don't stop there because I haven't answered my question. I'm trying to determine if the original function is increasing or decreasing. So now I need to use the fact that if the derivative is negative, that tells me that the original function is decreasing, right? So I have to finish out by answering that question there. Similarly, I want to do the same thing, but now for g of f of x. So again, that alters my formula a little bit because g is my outside function. So my derivative becomes g prime of f of 3 times f prime of 3. So again, f of 3 I need to do first because it's still part of a bigger composite function. So f of 3, I go to the f column, I go down to the value for the row 3, and I get a value of 2. So now I have g prime of 2 times f prime of 3. G prime of 2, I go to the g prime column, I go down to 2, I get the value of -3 times f prime of 3. So I go to f prime, I go down to 3, I get a value of 5. -3 times 5 gives me -15. So again, since my derivative is negative, that tells me that at 3, the original function is decreasing. And again, for part A and B, the original function is different. The original function for A is f of g of x, and for B, it's g of f of x. And we know that those are different things, right? It depends on how you compose them. So that's how we approach parts A and B. That's also how we would just find the derivative. If it said find, y prime at 3, then we would find the value. But that's how we incorporate the table into this particular formula. Now for part C, we're looking to find the equation of the tangent line to f of g of x at x equals 1. And as a reminder, in order to find the equation of a tangent line, we need a point and a slope. So here, let's find the point. In order to find the point, remember, we're going to plug in the y or the x value to get the corresponding y value. Okay, so y will be f of g of 1. That's going to give us the y value. So g of 1, if we come up here, g of 1 is going to give us a value of 3. So this is f of 3. And so f of 3, we go to the f column, we go down to 3, and that gives me a value of 2. So my point here is the point 1, 2. That's the point that the tangent line is going to touch this particular function. Now I also need the slope. So remember, to get the slope, I need the derivative. So for f of g of x, I'm going to do f prime of g, and now I'm interested in what's happening at 1, times g prime of 1. So again, it's just defaulting back to the default equation here. But now I need to figure out what this value is. So again, I start with g of 1 because this is still a bigger composite function. So g of 1, I go to the g function, I go to 1, and I get a value of 3. So I'm looking for f prime of 3 times g prime of 1. F prime of 3, I go to f prime, I go down to 3. That's going to give me 5, right? And then g prime of 1, I come up to g prime, I go down to 1, I get -4. 5 times -4 gives me a slope of -20. So now I have a point and I have a slope. So I'm going to put those together into y equals mx plus b. So let me see if I can find a space here for us to do that. So we have y equals -20x plus b. So I plugged in my slope. Now I plug in my point. When x is 1, y is 2. So I'm going to add the 20 over to the other side. And when I add 20, I'm going to add it to the 2. So I get b equals 22. Okay. So if my b is 22 and my slope is -20, that gives me a final equation of y equals -20x plus 22. So that is the equation of my tangent line for part C. So this is all sort of really conceptual right up front, where we're trying to take this generic formula and apply it to what we know about composite functions, what we know about derivatives, increasing, decreasing, equation of the tangent line. But the idea is that as we add in these new things, we have to always sort of connect it back to the things we've already learned, because anything we've already learned still applies to what we're doing here. Okay, so let's take a look at the next example. And using sort of a similar thought process here, we now have a graph. And so we're going to call h of x f of g of x and k of x g of f of x. So again, we're considering both compositions here. We want to use the graph below to find h prime of 1 and k prime of 2. So we're interested in what the derivative of the composite function is at these particular points. So I will again just write down our general formula. We have f prime of g of x times g prime of x for when we have f of x. And then when we had g of f of x, we have g prime of f of x times f prime of x. Okay, so I want you to think about how we can use these general formulas in conjunction with the graph to answer these two questions. And these should be numerical answers. You should get a number. And one thing I want to point out here is that you can assume that these lines go on in either direction forever, which I think will be helpful. So I'm going to give you about 2 minutes to see if you can figure out how we might figure out these two values, and then we'll go over it together. Okay, take about 30 more seconds. All right. So the first one we're interested is h prime of 1. So remember, h was f of g of x. So when we take the derivative of f of g of x, we get f prime of g of the number, and we're interested in 1, times g prime of the number. So our derivative that we have to figure out looks like this based on our general formula. So let's look at each of these pieces. Well, let's start with g of 1. So g of 1 means we're going to go to the g function and find the value when x equals 1. So that's right about at 4. So here we now need to find f prime of 4 times g prime of 1. So how do we get the derivative at 4 for f and at 1 for g? So if we wanted to find the derivative and we had a curve, we'd have to sketch in the tangent line and approximate the slope of that line. But we know that if a function is linear, that the derivative is the slope of the line. So we need to figure out the slope of the g function and the f function so that we can figure out what these derivatives are going to be. So let's look at the f function first. Here we can see that this crosses through the point 0, 8 up here, and also very conveniently 8, 0. So if we wanted to find the slope of this line and we did the change in y over the change in x, we would have 8 divided by -8, which means the slope of this line is -1. Okay. Similarly, if we were to find the slope of the red line here, we could certainly use this point where it crosses through. So this is the point 0, 2. And then we could certainly use this point here that we already looked at. So this is the point 1, 4. So when we calculate the slope of the line, we do the change in y over the change in x. So 4 minus 2 divided by 1 minus 0. That gives me a slope of 2. So f prime of 4 is the slope of the tangent line at 4 for f, and we know the slope of the tangent line has to be the slope of the line for linear functions. So this has a slope of -1. And then g prime of 1 is the slope of the line of g, because again, it's a linear function, and that's going to have a slope of 2. So we have -1 times 2. We multiply those together, and we get a value of -2. Okay. Now, similarly, if we want to find k prime of 2, we're going to have g of f of x. So then we set it up. So we have the derivative of the outside, inside stays the same, times the derivative of the inside, all at the value 2. So we start by finding the value of f of 2, right, this inner function. So f of 2, so remember f is this black line. So we go up here. So that gives us a value of 6. So we have g prime of 6 times f prime of 2. Now g prime of 6, again, is the slope of g at 6, but the slope of g anywhere is the same. It's linear. Everywhere it's got a slope of 2. So that gives a slope of 2. And f prime of 2 is the slope of f at 2. Because f is linear, it's got the same slope everywhere. So 2 times -1, again, leads us to -2. So in order to figure out these derivatives, we had to be able to apply the general function to get our map of what we were looking for. But then we also needed the slope of each of our functions to be able to talk about the derivative pieces of this formula. Okay. So again, these two particular problems, example 1 and example 2, are really asking you to connect everything you know about derivatives to this general formula for the chain rule function. Now, that's sort of bringing in everything from the past. The more common way that this comes up is algebraically. So what we're going to do is we're going to break down the chain rule into the different types of functions we've been learning. And we're going to learn how to apply the chain rule for algebraic functions. This is the more common way that you'll see the chain rule applied, and you'll have to do it. I would say 75 to 80% of the time you'll be doing this algebraically, okay? So we're going to start off with power functions, right? So I want to bring you back again to this idea that power functions, when we use the power rule, was functions that are polynomials or power functions, which means you have x in the base raised to a power, right? When we were doing the general derivative. So x squared, x to the 1/2, x to the 5th, right? Things like that. We had the power rule. So we have a chain rule power function if we have something complicated in the base and then raised to a power that is a number, right? So the variable is still down here in the base and it's raised to some number. So this is similar to the form that we had when we were doing the power rule. So this is the same as the function y equals z to the 10, right? Where z is 3x plus 4. So notice that we could write it like this, and it looks like the power rule. So that helps us visualize that we are talking about the power rule here. So how do we set this up? How do we work this out sort of algebraically? Well, there's two different ways that we do this, okay? So we're going to start with this particular rule where we're doing a substitution because that's going to help us see this power rule. Then after, we'll look at how we do it with the Newtonian method, and then from there you can decide which you prefer. So in order to get dy dx, the derivative of y with respect to x, that's what we want, right? We need to find dy dz and dz dx. What does that even mean? So here we're doing a substitution where whatever is in the base, we're going to call z. So here, z is 3x plus 4, right? We had that here, and we have that here, everything in the base, okay? And then we're going to rewrite y to be z to the 10th. So if this is z, then y is z to the 10th, because we're just substituting in what z equals. Once we make those two substitutions, we have two functions here that are now basic functions. Again, basic is not easy, basic is foundational. So from the first function, we can take the derivative of z with respect to x, which means we're taking the derivative of the right-hand side of this function. So the derivative of 3x is 3, and the derivative of 4 is 0 because it's a constant. Then from our second function, we can take dy dz, the derivative of y with respect to z. So when we do this, right, we have z to the 10th, we're just using a power rule. So the 10 comes down, z, and we subtract 1 from the power. So we have 10z to the 9th. So notice that these two derivatives, right, which are based on my substitution, are the two derivatives I need to multiply together to get the derivative I want. So by splitting up my function this way with a z substitution, and then finding the derivative of those pieces using the rules I already know, I can now multiply these two functions together to get the derivative I want. So the derivative I want, dy dx, is going to be 3 times 10z to the 9th. Now here, there's a couple things I need to do to clean this up. 3 times 10 is 30. And now my final answer, I don't want a z in my final answer. So what I need to do for one of my last steps is plug back in for z. So my z represented 3x plus 4 to the 9th. So the derivative of 3x plus 4 to the 10th ends up being 30 times 3x plus 4 to the 9th. Okay, so again, as a quick review of what we did, when you see something that is a power function, so something raised to a number, you let z equal whatever's in the base. Okay, then you rewrite the original function as z to the whatever power is given in the problem. Then you take each of their respective derivatives. So the derivative of this function and the derivative of this function. Then we multiply those two derivatives together and substitute back in for z. And that gives us the derivative to the original function. Okay? So I want you to try this method. Here we have the function f of x equals 3 minus x cubed, all raised to the 7th. So I want you to try this method. So again, you're going to have to figure out what is your z. And once you have your z, how do you rewrite your y? And then each of your respective derivatives to those pieces. And then you'll multiply them together and sub back in. Okay, so take about 2 minutes. See if you can figure out the pieces based on the problem we did before, and then we'll go through it together. All right, take about 30 more seconds. All right. So again, the first part of this problem is really recognizing that I have something that is in the form of a power function. So again, I have parentheses raised to a power. I have something raised to a power. My variable is still down here in the parentheses in the base. So now when I set up my substitution, your z is whatever was in the base that's raised to the power. So 3 minus x cubed. Then we rewrite our y as z to the 7th, because we said that z is the base. So now we have z to the 7th. Then we need to find each of their respective derivatives. So here, 3 minus x cubed, the derivative of 3 we know is 0. And then for minus x cubed, make sure that you don't lose the negative, right? So when the 3 comes down, we have minus 3x to the 2 power. For our y function, we have z to the 7th, so the derivative here will be 7z to the 6th. And again, from what we talked about before for the chain rule, if we were to multiply these two derivatives together, we will get the derivative we want. So negative 3x squared times 7z to the 6th. We have to do a little simplification here. So the 7 and the negative 3 we can multiply, and that'll give me negative 21 Then I have my x squared term. And then I also have z to the 6th, but I don't want z in my final answer. So I substitute back in for what z represents. So I'm going to use parentheses since there's more than one term here. So we have 3 minus x cubed to the 6th power. Some really important things about simplification here. Since z is raised to the 6th power, the entire z function has to be raised to the 6th, so you have to use parentheses here. We cannot bring in the negative 21 or x squared into the parentheses in any way because of this 6th power. So we wouldn't bring those in. So we would leave our final solution like this. When you have your final solution, you want to make sure it's the same variable everywhere and not two different variables. That's why we have to substitute back in at the end. Okay, so keeping that in mind, this is sort of what's happening in the background, the process, right? But if z is a differentiable function of x, then the derivative of z to the n equals nz to the n minus 1 times dz dx. So this looks a lot like our power rule, but what this is saying is that we can treat this function like a power rule, like we had from before, where we can bring the power down out front and subtract 1, right? Where everything inside stays the same, and then just multiply by the derivative of the inside. So what does that look like? So if we were treating it using this rule, which is a little more Newtonian based, here we would start with this power of 7, and we'd say, okay, well, if I'm going to take the derivative, the 7 will come down in front, everything inside will stay the same, and I subtract 1 from the power. So I just deal with the outside function first, okay? I just deal with the power. But then I have to remember to multiply by the derivative of the inside, okay? So the derivative of the inside, I have 0 minus, so I have minus 3x squared. So this is, this is inside, this is derivative of inside, okay? And then you would still take one step to simplify, right? So here we still get negative 21 x squared. I bring that to the front, 3 minus x cubed to the 6th. So thinking about it as a power rule in general and just bring down the power is a little bit faster, but you have to remember what changes and what doesn't. So here, right, we have to remember that when you do the outside part, the inside stays the same. And then we have to remember to multiply by the derivative of the inside. If we can remember all of those pieces, then setting it up this way is faster. If we find that we're forgetting what happens in here or what happens over here, then doing it this way ensures that we don't miss anything along the way. So this is sort of two different approaches to the same problem, depending on which one you think will work best for you, okay? So now we're gonna do some practice problems using the power rule here. So we'll start with this one. We have sine x plus 2 all raised to the 5th power, okay? So I want you to take about 2 minutes. You can use either method. You can try to think about it as a power function, inside, outside, or you can set it up with a z substitution, whichever one you think will work better for you. But take about 2 minutes and see if you can figure out the derivative of this composite function. Okay, take about 30 more seconds. All right. So regardless of how you approach this, you should get the same final answer. And so I'm going to do this with the second method since we practiced the Z method and then sort of switch back and forth between the two. So how do I approach this? So first, again, I notice I have something raised to a power. And that tells me, okay, this is a chain rule, which has the structure of a power function. So now I'm going to treat this like a power function. I'm going to say, okay, for a power function, the power comes down and I subtract 1 from the power. Okay, so 5x to the 4th. But instead of x, everything inside stays the same. Okay, so that's the outside structure of the power function. But then I have to remember to multiply that by the derivative of the inside. So when I think about the inside function, that's the part in parentheses, not the power. So the derivative of sine, we remember is cosine. And then the derivative of 4 is 0 because it's a constant. So I get something that looks like this. And just so that you know, typically the way that we write answers on sort of quizzes and things like that is we write them in increasing difficulty. So any constant will come first. Then we'll go and look at each parenthesis and see how high their power is. So since cosine x is just the power of 1, we would write that next. And then sine x plus 4 to the 4th. So this is the same. These are the same two things. And if you had done this slightly differently in a different order, you would essentially just want to look at each factor and make sure it lines up with one of the factors in the answer to make sure that it's the same thing. Okay, so that's what the first derivative of this function looks like using that chain rule. Let's go ahead and we're going to try 2 more applications here. So the first one is another find the derivative. So again, we see parentheses raised to some sort of power. So again, we're going to apply that rule and try that again just for good practice. And then in example 4, we're going to find the equation of the tangent line to the function 3x plus 10 at x equals 2. So again, we think back to what we need to do to find the equation of a tangent line. We need a point, we need a slope. The point we know how to get. The slope, we have to take the derivative. And as a reminder, the square root is the same thing as a 1/2 power. So we end up with a chain rule to find the derivative in order to find that slope. Okay, so I'm going to give you about 5 minutes to do these 2 problems, right, where we practice our power rule, chain rule, and see what we can figure out. Try to write things out carefully so that if you do make a mistake, it's easy to identify where you may have gone wrong. But just think about what we've done the last couple problems and hopefully you'll be able to work through it. Okay, so take about 5 minutes and then we'll go through them together. right, take about 30 more seconds. All right. So starting with example 3, this time I'm going to do it with a z substitution just to sort of go back and forth. Again, if you did it the other way, you should still end up with the same thing at the end. So if we're going to set it up as a z substitution, again, our z is whatever is in the base, which here is what's in the parentheses. So that's e to the x plus x squared minus 1. And then we rewrite our function y as z to the negative 3. So z to whatever this power is, which here was negative 3. Then we need to find each of their respective derivatives. So here, because we're separated by addition and subtraction, we go term by term. So we get e to the x plus 2x, and then we would have a 0 over here. And then the derivative of z to the negative 3 is negative 3z to the negative 4. Remember, when you have negative powers, they become more negative when you subtract one from the power. So now we want to multiply our two derivatives together. So again, because this has more than one term, I'm going to use parentheses. So e to the x plus 2x times negative 3z to the negative 4. And then again, I'm going to do just a little housekeeping here. So this negative 3, which is my constant, I'm going to pull to the front. So I have negative 3 times e to the x plus 2x. And now here I have z to the negative 4. I don't want a z in my answer, so I have to go back to what z was and substitute in. So I have e to the x plus x squared minus 1 to the negative 4 power. Okay, so again, if you did a different way, you're just going to look at your factors and make sure that each of these three things is part of your solution, and then you should be good to go. Okay, so now that we've been practicing computing these power chain rule derivatives, we can take it a step further and find the equation of the tangent line, right? So again, we've done tangent line problems before, and now we're just changing the type of function we're looking at, but the process is the same. So again, in order to find the equation of a tangent line, we need a point and we need slope. So to find the y value here, we're going to plug a 2 into our function. So if we plug in a 2, we get the square root of 3 times 2 plus 10. Okay, so 3 times 2 is 6, plus 10 is 16. The square root of 16 is 4. So when y equals, or when x equals 2, y equals 4. So my point here is the point 2, 4. I also need the slope. So that's where the derivative comes in. And so here I have to rewrite this function first to deal with the derivative. Because remember, when it's in the square root form, I can't do anything with that symbol. So here we have 3x plus 10 to the 1/2 power. So now if I want to find the derivative, I can bring the 1/2 down in front from my power rule, where everything inside stays the same. And I subtract 1 from the power. So to the negative 1/2. Okay. So now I have to remember that that is the power part of this, right? So that dealt with this. And I have to multiply that by the derivative of the inside. So here I look at the inside and I have the derivative of 3x is 3 and the derivative of 10 is 0. Okay, so my derivative looks like this. And now to get the slope, I need to plug in the x value that I'm interested in. I am going to simplify this before I plug in. That's just a matter of preference for me. If you would like to plug in like this into your calculator and you're comfortable doing so, you can feel free. But I'm going to bring that 3 to the front to multiply with the 1/2. And then I'm going to bring this term back down to the bottom. And I'm going to turn it back into the square root. Okay, so I have 3 over 2 times the square root of 3x plus 10. You do not need to do this step. I just prefer to simplify things before I plug in. But if you are comfortable with your calculator, you can certainly plug in the 2 in this step. So when I plug in a 2 here, I get 3 divided by 2 times the square root of 3 times 2 plus 10. So again, that is 16, and the square root of 16 is 4. So I have 3 over 2 times 4. 2 times 4 is going to give me 8. Okay, so my slope here is 3/8. Part of the reason why I simplified is because I don't want this to be a decimal. I prefer working in fractions. And if this comes out to be irrational, I need to know what the fraction is. So that's another reason why you may want to simplify. Okay, so now I have the slope of the line and I have a point on the line. So I'm going to put it all together. So I have y equals 3/8 x plus b. I need to solve for b. So I solve for b by plugging in my point here. So y is 4 and x is 2. Okay. Got to be careful with our fractions here. So I'm going to turn this into its own fraction for a second. So 3/8 times 2 is going to give me 6/8 plus b. So I have to subtract 6/8 from both sides, right? So I have 4 minus 6/8 equals b. If I want to deal in eighths here, I have to turn my 4 into eighths. So I have 32/8 minus 6/8 equals b. So 32 minus 6 is 26. So I have 26/8. Okay. So now I put it all together for my final equation here. And I get y equals 3/8 x plus 26/8. So that is the final equation of my tangent line. Now, this seems more difficult than the other tangent lines we've looked at. Why is that? 1, the derivative is more complex. 2, the numbers that we get out for things like slope are not integer numbers. Whenever they're not integer numbers, it makes the problem a little more tricky, and we just have to be a little extra careful as we deal in fractions. Okay, so that's what that one looks like. So now we're gonna talk about how we can take what we've learned about power functions and think about other types of functions the same way. So the next type we're going to look at is exponential functions. So we can break things down similarly, but the first part is recognizing that the variable is up in the power, right? Just like with any exponential functions, when you have like 2 to the x or 3 to the x, we know it's exponential because the variable is in the power. Here, the variable's up in the power. It just happens to be more complicated than just a single variable, right? But we still have the variable in the power, which is the key thing we're looking for to recognize that we're doing a chain rule exponential type. So similarly, right, what we can do is we can do a substitution where the thing that's supposed to be just a single variable in the power is going to get substituted in by z. So if you have a number raised to something complicated, then we have this exponential form, and our z is whatever's up in the power. And then the rest of the process looks pretty similar to what we were doing before. So here, if we have z equals 7x squared, then our y would be 4 to the z, right? Because we said that z is whatever's up in the power. So then we substitute in what the z was. Now we want to find each of their respective derivatives. So the derivative of 7x squared is 14x. And the derivative of 4 to the z, our exponential rule says is 4 to the z times the natural log of the base. which here is 4. So then, just like before, we're going to multiply these two things together. So we get 14x times 4 to the z ln 4. And just like last time, we don't want a z in our final answer. So we get 14x, 4 to the 7x squared, so we substitute back in, times ln 4. So these are the three terms that we have from multiplying together. So we're applying the same process. The difference here is how you pick your z. So we recognize it's exponential, and therefore we pick our z to be whatever the power is. Then we rewrite y, we find each of their derivatives, we multiply them together. Okay, so let's try one out here. So take about 2 minutes. See, this says e to the sine x minus x squared. So see if you can figure out what your z should be in this function, how you would rewrite your y, each of their derivatives, and then multiply them together. Okay, so take about 2 minutes, and then we'll go through it together. Okay, so let's take a look at this one. So here, again, I recognize that my variables are up in the power, right? They're not in the base, they're up in the power. So this is an exponential form. So when I do my substitution, my z is going to be whatever is up here in the power. So in this case, that's sine x minus x squared. Then I rewrite my function as e to the z because I'm calling z the power. Now I need to take each of their respective derivatives. The derivative of sine is cosine. The derivative of x squared is 2x. So that's the derivative of that first z function. And the derivative of e to the z is just e to the z, right? Because that's our special case for exponentials. Now I need to multiply my two functions together. And again, because this first one has more than one term, I'm going to use parentheses. So I have cosine x minus 2x in parentheses, the whole thing, times e to the z. But I don't want a z in my final answer. So cosine x minus 2x times e, and now I substitute back in sine x minus x squared. Okay, so that's how we set up our z substitution. Now, similar to the last one, we do have a little bit of a shortcut if we want to work through conceptually how we apply what we know about exponential derivatives to chain rule type of functions. So if everything's differentiable, which it will be for our course here, if you're going to take the derivative of a to the z, where z is something differentiable, but you have some exponential form, then you're going to have the same thing back, a to the z, just like we started with, times the natural log of the base, times the derivative of the power. Okay. Similarly, if you have the derivative of e to the z, then we get e to the z back times the derivative of the power. So let's look at the problem we just did. So what this rule says is that if we're going to take the derivative of a chain rule that has a base e, we're going to get the same thing back. So here, e to the z, e to the z. So e to the sine x minus x squared times the derivative of the power. So here I notice that the power has two terms. So I use parentheses. The derivative of sine is cosine. The derivative of x squared is 2x. So here, all I had to do was copy down the original function and then separately consider what the derivative of the power will be. And I get the same thing that I did with my z substitution. I want to point out here that the power of e does not change, right? So I started with e to the sine x minus x squared, and any term that has e in it still has that same power, okay? So let's try one of these e forms, okay? Or I guess one of the exponential forms, I should have said. So we have pi times 5 cos x, or pi to the 5 cos x. So you can either use a substitution or you can reason through the exponential form. But I'd like you to take 2 minutes and see if you can think about what the derivative might be. And again, we know it's exponential because the variable is up in the power. Okay, so take 2 minutes and then we'll go through it together. All right, so let's take a look at this one. So if we try to apply the shortcut method that we just looked at, what would that look like, right? So we get the same thing back. So we have pi raised to the 5 cosine x times the natural log of the base. That's the first part, right? So that's like our a to the x form, same thing back, times the natural log of the base. But for the chain rule, we have to remember to also multiply by the derivative of the power. So we have to multiply by the derivative of 5 cos. So the derivative of cosine is negative sine. So we have negative 5 sine x. Now again, if this was going to be presented on a mini quiz, the likely way you would see this is that The -5 would come first, then all the linear terms. So then we'd have ln of pi, that's also a number, times sine x times pi 5 cos x. Okay, so as long as we have all those terms in there, then your answer is good to go. Okay, so I would highly recommend that you start working on the homework and do the problems that include power functions and exponentials. We'll do 2 more exponential problems on Thursday and then do natural logs and sine and cosine chain rules. Okay, so have a good rest of your day, and I will see you all on Thursday.